A samara is a winged seed, and so many of us are familiar with a maple seed dropping from a maple tree, and it rotates down to the ground. After World War II, a fellow named McCutcheon, observing this behavior and being an aerodynamicist and active in airframe development, developed a structure that mimicked the flight characteristics of a maple seed. And it didn't go very far because the control strategy, the incorporation of gyros, which at the time were spinning titanium mass, electromechanical, really hampered the development of controls. Fast forward to around 2007, 2006, researchers at the University of Maryland, one in particular named Evan Ulrich, were interested in this phenomena. In fact, Evan, now working at the Aerospace Corporation in the controls laboratory, spent 2 years of his 5-year PhD program characterizing the descent of a maple seed very, very exquisitely with special photography, controlled drop cylinders, and I think probably understands the aerodynamic behavior of maple seeds better than anybody on the planet. So the next 3 years of his PhD work were focused on building a maple seed single wing variant drone. And the problem was complex because computational fluid dynamic models for things of this scale didn't exist and still don't exist, because at this scale there are turbulences that make the characterization of airflow very, very difficult. In fact, he's commented to me, it's another PhD thesis if somebody wants to characterize the airflow around such a device. The reason that this research has progressed and is of interest is that the aerodynamic characteristics of a maple seed type drone provide about twice the efficiency of a typical quadcopter drone. And the efficiency of these devices is a function of the rotor area. And you can imagine in a quadcopter with 4 small propellers what the area of those propellers is versus a device like a maple seed that's rotating, and you look at the area of this airfoil compared to 4 quadcopter propellers, and you can pretty quickly get a sense of the aerodynamic efficiency. So what changed between the early 50s when McCutcheon did his work and several others over the next several decades? What's changed is that you can buy for $80 analog device solid-state gyros with 5,000 degree per second saturation thresholds, solid-state devices, sensors, microcomputing now that can do the controls in a much, much more capable way. And so Evan patented a single wing version of a maple seed drone. He's patented N+1 wing versions of this drone, and we're talking to several potential customers and interested in licensing the technology. What I think the drawbacks of the technology is that in a rotating platform, instrumentation packages, videography and so forth, for example, videography either needs to be despun below the rotating platform, or with signal conditioning, you can construct 360-degree field of view images with this rotating video camera, which is interesting. One of our customers is looking at the technology for launch range surveillance. So you've got turbulent wind and you want extended time of flight for these vehicles, and the arrow seed or maple seed type aerodynamic architecture provides much greater stability in turbulence than a traditional quadcopter, and also nearly twice the time of mission. Its rotating characteristic also makes it of interest for people sampling gaseous species, where the sample rate of the gas that you want to sample is much, much higher than, say, a fixed-wing drone or a quadcopter. So by virtue of this rotation, you're getting a lot more atmosphere into your sensors. So your talk was of interest to me, for example.